That'll get worked on in the background. In the meantime, you should have the documents for question 3. Yeah, we'll just crack on with that while I fix in the handwritten camera.
Is the period 12?
Yeah, the period's going to be 12. A couple of ways you could have done that. I'm assuming you probably just looked at it. More or less just looking at when it repeats. Because yeah, that's more or less the approach I would have used there. Cool. Alright, period 12. Next up, find the values of t where f of t equals 0. So just solve f of t equals 0. Reminder, this is CAS.
Is this just 0, 4, and 6?
0, 4, and 6 is correct. Yeah. Nice and easy CAS solve. Nothing really to it. Yeah, just chuck the function, let it equal 0, and set your appropriate domain. Easy. Let's see. Maximum strength of the dual tone frequency signal. So it's worth pointing out the graph F is the graph of a dual tone frequency signal. So that means that the signal strength would be on the y-axis. In other words, it's asking you to find the maximum y value of the function. Can't open the documents. That's curious. As in through Zoom, you can't open them up. Huh. Okay. Okay, let me give you a link to the VCAA website. You'll be able to pull them from there as well. Actually, that won't work too well because that means you won't get the solutions that I've got. So what I'll do instead is copy a link straight from here. Should do. Okay, that probably works. See if that gets you to the 2019 folder. Looking for the exam 2. But okay, so maximum strength of the signal strength being on the y-axis, so it's basically asking you what's the maximum y value. You've got a lot of options there. But the graphing tool, that can help you find it pretty quickly. You've got things like fmax, you've got derivative 0, since they are turning points. All these, you can see them on the graph, the maximums are all turning points. So all these approaches could work. Need it to 2 decimal places. Are we stuck on the procedure? What's going on? Okay. So one of the ways, if you have a look at the camera that's now finally made its way in, you could just fmax on the function. So define the function. We've got x equals a certain value. I'm just shoving that x back into f of x to obtain the the exact y value, but then we're going to control enter on it, because that way you get the 2 decimal places like we're looking for. 1.76 is what we're looking for there. I've just put in a whatever domain, just enough to find that first peak. Like if you look back at the screen share, for instance, I can see there's clearly a peak around 2, so I've just done the 0 to 6 domain, kind of like copying from B, basically, because that guarantees I'll definitely touch that peak. That's because I can look at the graph anyway. If I didn't have any idea of the graph, I would probably do it over a period, so from 0 to 12 instead, and that would definitely guarantee it. The other approach could be the graphing tool, which I don't actually have a picture on, but that's what I did there. You just plot f of x on the CAS and then use the tool to find the maximum there. In fact, doing the graph would have been, may or may not have been helpful for D. Find the area of the graph between the graph of f and the horizontal axis. You kind of already have a picture. It says it from 0 to 6, so you're looking for this big thing in here and this little thing in here, essentially, because you've got the graph of f that binds it and the x-axis that create the shapes that you're trying to find. Has everyone else been able to get a copy? Because you might need to scroll back and forth between the sections. Let me know if there's any issues opening those. If that Google Drive didn't work, I could also give you the VCAA website. In fact, I might as well just do that now while you guys think. Yeah, so if that Google Drive is still stuffed, you've got the VCAA website here as well. If you just go to the drop down 2016 to 2022.
Is it 12 on pi?
12 on pi, let's have a look. 12 on pi is a little bit off. I'm imagining you probably didn't fix up the
Right.
bottom bit to be
The
positive.
negative.
Yeah.
Yeah, okay.
So pretty close then. Yeah, you want to then do your definite integral from 0 to 4 to get the positive bit, 4 to 6 to get the negative bit. But yeah, as we've just said, because area under the curve underneath the x-axis is considered negative, two things you could try. One is to just chuck a negative on the thing. That flips your negative to now being a positive. The other would be what? What else could you do to flip it around?
Is it flip the terminals?
Flip the terminals, absolutely. So instead of doing 6 on top and 4 on bottom, you do 4 on top and 6 on bottom. And you would leave this as a plus. Yeah, don't do both because then you flip negative twice back to being what it was. Yeah, that's that. And that's just, enter that in the CAS and you're sorted. Okay, for this one, I'll need to give you something to work off. So let me give you the x dash y dash equivalents there. That one there means we have x dash is ax plus c, and y dash is, I'm assuming, by plus d. Yeah, that's good. Yeah, those are the transformations that matrix is describing. Find a, b, c, d given a particular set of integrals. So in this case, you've got 0 to 2 and 2 to 6 for your two functions g of t, where g is the transformed version of this function. So after I do my subbing in of the transformation terms in there, I get g of t. And we're applying that to these integrals. This gets quite tricky, I would say. I wrote well, I wanted to say recently, but it's been months actually now. I updated the notes on definite integral properties. Because I think just by looking at it without thinking too hard, you're going to have to figure out a little bit about how the boundaries of the integral change depending on transformations. That's a fairly niche topic, but as you can see, it does show up. So I think what I'll do is I'll pop that doc specifically in the chat. Definite integral. And if that's, if that's not downloadable, it'll be in the school under the calculus integrals, definite integral, if you can't go it from there. I saw this one in an interesting way. Yeah. I mean, a good point of call would be to try and figure out what G actually is. So applying your transformations knowledge and then shoving that back into f of x would be a good start. Just a reminder, of course, you need to get x and y on their own before subbing it. So you'd get something to the effect of x equals x dash minus c on a, y equals y dash minus d on b. So then instead of having y equals your function, f of x, you will now have y minus d on b, f of x minus c on a. And then, well, just doing your rearranging here, y equals b times f of x minus c on a, plus d, and that is the g of x. The other thing you might want to start considering is that you got 4 unknowns, and so probably going to need 4 equations to solve those. You might be able to do it as a full simultaneous with 4 separate equations, although I will say the way I personally did it was one pair of equations gets the first 2 solutions, and then another pair of equations gets the second 2 solutions. So even though you probably could still do it with 4 in a big stack on your CAS, there is a way to do it as 2 and 2. Anyone making any progress they'd like to share? It's definitely on the tougher side, so I wouldn't be shocked if there was a bit of a blank. In fact, I'm curious, what does the exam report say? Pass rate. Yeah, we'll go into it. I'm just real quick want to double check and see what the pass rate on this was. So what was this? This was 3E. Let's have a look. Oh shit, 10% for 2 marks. Not bad. Cool. So what did I do? So as you see, starting out with our x dash y dash thing, good start. We do eventually do that whole rearranging, as you see, but one of the first things I did was a little bit strange, but it has some logic to it, which is you sort of look at the 2 terms that are in this second section, and you kind of compare that to what you had initially. Because basically what the whole premise of this question is we're going to do some transformation, and then this new set of integrals is going to be the same area as the old set of integrals. So I look at these 2 things here and here, and what I'm essentially doing is picking out each integral and marrying it up with the equivalent on the other one. Like for instance, the 0 to 2 here is a distance of 2 on the graph. That's purely to sort out this. Right, like in our case we had 4 to 6. In their case they had written it as 0 to 2. Right? There's no yeah, you can look at the relative spacing of the terms and then figure out what each integral is sort of meant to accomplish as far as what part of the area on the graph. Like you can see this one has a spacing of 4, this one also has a spacing of 4. And so in that way you can marry them up and say, oh, this one is a transform version of this one. And so in that way I'm saying, yep, these 2 serve the same purpose of finding the same area, so I'm going to rewrite them to become more equatable to each other. So instead of having like a negative here and 4 to 6, I'm going to rewrite it to make it in the same sort of idea here where you flip the terminals. So instead of doing 4 to 6, I'm going to do 6 to 4. And now I can say, cool, okay, this is my old, this is my new, and so the new is obtained by putting a transformation on the old. That's how we shove in, like, for instance, the 4 here into the ax plus c, because that's the old value, and then whatever that equals gives you the new value. that gets you a set of simultaneous, which can pretty quickly figure out that A is going to be 1 and C is going to be -4 there. It's a bit of a unique approach, that one. Any questions so far as to how we got a set of solutions for A and C? If that bit's confusing, the second bit is a different approach that I believe could work to also solve this this set as well. You don't have to have this whole idea of the flip and then equate like this. The second idea was, okay, cool. We can now do our transformation, actually apply it. Get the x and y on their own, shove it into the function, obtain g of x. Now, this is what it would look like if you had none of the solutions, but this is what it looks like when you have a few of them. We had the a and the c, for instance, getting us x plus 4 after you sub in all of this. From there, what I've done is compare the relative areas that they should have. So I understand most of us probably would have just done this in the CAS and got 15 on pi. What I would then do is go back to these and figure out what was the individual areas for each of these, and then make those the equations for G. Because remember, G has to have the same proportions that F does if it's going to add up to the same relative or the same actual area. So I recalculate what these were individually, 3 on 2 pi and 27 on 2 pi, and then they have to be the same as the G versions. And so what you then do is you go through and put in the G functions and make them equal the areas that you know you want them to equal. So although there's these transformations applied to it, we know they have to still equal the same net area to add it all up. And yeah, when you simultaneously solve that, you will get the B and D values. Now, the funny thing about this question is that these weren't actually the figures that the exam report quotes. It just says, it gives one set of solutions and then just says, hey, there's others, by the way. Like, in fact, yeah, what was I looking at? There are other solutions. So there's a bunch of ways you could have approached this. I'll just do a quick pulse check to make sure at least this is making sense so far. Even if it's just broadly making sense, because this is definitely one of the separator type of questions. Very uncommon. Cool. I haven't actually looked at this, so let me see if I can get my head around what was going on here. Reflect F in Y and translate 6 left. Oh, they're just describing what those would have ended up being. A equals -1, B equals 1. Okay, so they're not actually describing how they did it, they're just describing other possible sets of transformations that could achieve it. Yeah, okay. So without getting into too many specifics, what I'll do is I'll propose like one more way that you probably could use to solve it, and that would have been the definite integrals doc that I dropped down, which is as follows. Let's pull that up. So all of these. This describes what happens when you, well, 5 and 6 specifically, describes what happens when you have, oh, even 2, describes what happens when you have transformations applied. Right, like you got your K, your dilate factor. What can you do with that? You got your C, another dilate factor. What can you do with that? Translations, what do those do to the function? And so what you could potentially start working towards would be to say, okay, cool, I've got 0 to 2, which should be matching up to the 6 to 4. Oh, sorry, the way around, 4 to 6. What I could then do is, yes, this initial flip thing to make them more comparable, and then say, oh, okay, what's happened here is it's been shifted right. No, hang on. So we're starting here, we're going here. It's shifted down or left by 4. And so when you look at your, instead of doing like x dash y dash stuff, you could start saying, oh, well, it's just a shift left by 4. And there's clearly no x dilation because otherwise you would have a different spacing. So you wouldn't necessarily need your x dash y dash stuff to figure that out. You could just sort of flip it around and go, oh yeah, this is shifted 4 down, this would also be shifted 4 down. And you could probably apply the same thing here just by going purely based on all of these rules and setting up your equations that way. Won't get into too many more details there because I'm not 1000% sure it's going to work. So you've got at least one approach that definitely works. Cool. All right, that's that one. Part F. The rectangle bounded by the line y equals k, horizontal axis, and x equals 0, x equals 12. So firstly, what does that mean? Y equals k, so there's some value of k that you can draw a horizontal line on this graph, and the area you're looking for is between 0 to 12. So you're going to draw some k that's going to give you some ceiling, or maybe a floor, depending on where you put it, of your bound area. And you're doing it in a way where it gives you the same area between oh, the rectangle. Sorry, my bad. You're doing a rectangle. You're not just drawing F and making it a ceiling. You're drawing your K and actually drawing a box. So for instance, if you drew it as K equals 1, you would have 1 by 12 as your area. It's a rectangle that's formed by the K. I might have a picture of it. That's better. So like if you shoved your K there, you would have this rectangle. And the idea is that you want to choose your value of K, the ceiling or the floor of the rectangle, such that it's the same as all of these little bits of area added together. I believe that's what it's asking. Same as the area between the graph of F horizontal for one period. Yeah, and that's one period. So you want to have it, this is the same as that plus that plus that plus that. The fact that it's 2 marks should be a bit of a warning sign. It's, looking at this graph, you might be tempted to consider symmetries. I feel like if there was a symmetry involved, it would be a 1 marker. Like for instance, all of the negative portions adding up to be the positive portions, that would make it 0 and therefore, well, you'd probably choose k equals 0 under those circumstances. That wouldn't get you 2 marks, though. So that's probably your warning to double check that there actually is some symmetries in there.
This is the answer 5 on 2 pi.
5 on 2 pi is correct. Yeah, very good. How was that? How'd you do it?
So you want to find the area between the horizontal axis and the graph from 0 to 12,
Mm-hmm.
which is a combination of four integrals. Wherever if there's a negative area, I just look at the terminals.
Yep.
And then whatever you get, you want to divide it by 12.
Mm.
The answer, because that will give you like the k value, the height of the rectangle.
Divided by 12 gets you the... Yeah, okay. That's cool, because, yeah, because area of the rectangle bit would be like a length times width, and so when you're dividing it by 12, yeah, you're getting the other term. That's an interesting way of going about it. Yeah, taking this and dividing it by
Wait, can I
12.
ask how you would have done it? Because
Oh, I just would have had the two area equations make them equal each other. So you got 12 by k for the box, and then just like you described over. Um, oh, there was symmetry. Why wouldn't have you just chosen? Oh, right, because area 1 was this bit, and doubling it. Oh, right, I misunderstood. Yeah, I was treating these as negatives as actual negatives. Yeah, my bad. Yeah, so you just create your two area equations. Um, there were symmetries, my bad. I just misunderstood the premise a little bit. But yeah, create your two area equations, whether you set up four integrals or you just double the first one that you created earlier, and then make them equal to each other. That's effectively what you've done. You figured out this 30 over pi, and then you divide it by 12. That would also get you k. It's the same math, but the logic to get there was slightly different, if I'm not mistaken. Fair enough. Sweet. Probability. Question 4. Lorenz birdwing. Probability density function is given by the piecewise. Find the mean lifespan. So in other words, just mean of what you would do when you normally have a piecewise function. The fact that it's a Lorenz birdwing butterfly has next to nothing to do with how you actually solve it. Which is kind of what I like about probability. And I guess most of the application questions. Doesn't really matter what the scenario is, as long as you can just know, hey, oh, it's actually talking about this thing. But double check your formula sheet if you would need to, or I guess even your notes because it's tech active. Pretty sure it's definitely in there. Mean of this probability type. But let me double check. Yep, definitely there. And on 3, let's have a look. Yeah, exactly right. Precisely. So find the mean. Why'd I put this in a solve? That's weird. Anyway, you wouldn't actually have a solve. You would have just had x f of x. Obviously, just define f as that. This is continuous, so you would use the continuous way of solving the mean. It shouldn't be a solve. Ignore that bit. Since it's 2 marks, you probably would want to write out the integral as well. That way you can get your mark for working as well. But yeah, nice. In a sample of 80, how many butterflies are expected to live longer than 2 weeks? Talking samples now. We're taking a sample of 80, so we're at least guaranteed to be going into some sort of discrete. because now we're talking about the individual butterflies rather than as a full population. 73.0. Yeah, let me just... So nearest integer, you probably wouldn't put the 0.0 on that one. That may or may not cause them to dock the mark. Probably might. So yeah, just probably want to give it a 73 instead. As for if it's good, yeah, so how many butterflies will be expected to live longer than 2 weeks? Yeah, so just set your integral as appropriate. So 2 to 5, because you're longer than 2 weeks, up to 5, and then because you've got 80 of them. Once you found that probability of living longer than 2 weeks, you then multiply by the number of things you want to see live longer than 2 weeks. So you're essentially doing an E of x, but you need to calculate the p. But it's in the discrete version. Or I guess, said a bit better, you need to use continuous to find your binomial probability. Binomial specifically because you either live longer or you don't. It's one or the other. Cool. Part C. What is the probability living for at least 4 weeks, so 4 or more, given that it lives for at least 2 weeks, so 2 or more? If you solved B, you could probably solve C quite easily still. Using very similar approaches. You just don't really need like your E of x, since we're no longer caring about like a number of them. To 877. It maybe I've rounded it a bit off. I've got 0.2878. Let me just double check who's got the right rounding. Yeah, 2878 was what that was looking like. So maybe... Oh, cool. Okay, so you spotted what was wrong. I was thinking maybe you might have plugged in the old answer rounded for the denominator, the 2 to 5, because that would have caused a bit of a rounding error. You'd rather plug in the full, like exact, the integral version rather than the decimal. But yeah, close enough. It was just a rounding issue there. As far as what was done, it would have been a conditional probability formula. So you've got probability of living longer than 4, well, 4 or more, given 2 or more. That means you're going to want to find the intersection of the two things and divide by the conditional, which is living 2 or more. These are both pointing in the same direction, so in this case, because it's the greater than sign, you're going to simplify that down to just being greater than or equal to 4. This denominator, as I sort of said before, we've already figured that one out. We did x greater than or equal to 2 over here. When you do 2 to 5, 4 to 5 is, well, the exact same thing. You take your two fractions, stick one on the other, and yeah, conditional probability. Part D. the wingspans are normally distributed. Mean and standard deviation are given, as always. Well, in most cases. Find the probability of between 16 and 18. This one should be a freebie. 4 decimal places. There's two key functions you'd want to use for normal distribution stuff. It's either a CDF if you're trying to calculate probabilities, or you're using the inverse normal when you're trying to find. I mean, you use it for a lot of things. Typically, what's when you're trying to find an x value specifically. 0.1512 using a CDF, that's it. Yeah, because we're trying to find the probability between a certain domain. That's a CDF. Yeah, normal CDF, give the mean, standard deviation, lower and upper. Casio and TI-Nspire have the exact same, well, more or less the exact same thing. I think they flipped the mean and standard deviation spots, and on the Casio it's, no, it might still be called normal CDF on the Casio. Maybe normal CDF. Anyway, same thing. Cool, well done. Part E. Very small is if you are in the smallest 5%. And oh, okay, so figure out how big a wingspan could be for a very small bird. Oh, butterfly. So, you got your smallest 5% on the normal distribution, you're all the way on the left in the 5% range. How big can you possibly get up the x-axis scale before you're out of that range of being considered very small? So if you remember what I said earlier about two distinct functions, and you use them for different purposes, we're not doing probabilities here. I mean, the probability stuff will come into it, but the thing we're trying to solve is not a probability. It's a something. $17.55. You got that. I imagine you might need to flip the tail. I think you're probably pointing right when you should be pointing left, or vice versa. Because smallest 5% means you're in the left part. I feel like the number you've given me is on the right hand side. So if we maybe do a little visual of what that would look like. You got your mean, and the smallest 5% is over here. And a bit of a error correction that you can do is, if you notice that the mean is 14.1, once you have this diagram, a number like 17.55 suddenly seems a bit silly, because you got to be over here. You want to know how big can we possibly be before we stop being very small, which would be, something like in here. You're looking for that particular coordinate there. So that's just a bit of error checking you can do when you're in the exam. Double check with the picture. I'll pretty much literally always draw a picture for normal distribution stuff. Even the simple shit like doing the CDF. I would still draw it to make sure that I'm doing more or less the right thing there. So what I think you might have done would have been you could have picked R instead of L, because you're using Casio, I think. That would have given you this one over here. Or you flip the 5% to a 95% when it should maintain as 5% L. Maybe show that actually. Yeah, here. So if you're Casio, you want L and 0.05 on that one there. For TI Inspire, you have to be left, so make sure you definitely give the 0.05. But this would have also worked over here for Casio if you're choosing R and 0.95. Fair enough what's going on there? Awesome. Okay. Each year, a detailed study is conducted on 36, a random sample. Very large, 17.5. There you go. So there's your number, 17.5. That's your top 5%. The probability of the wingspan for any Lorenz greater than that is approximately 5%. Makes sense. Find the probability that 3 or more of these butterflies in that random sample are very large. So you're given probability of being very large, and we want 3 or more of the 36 to be very large. Binomial CDF, yes. 0.2947, yes, absolutely. So binomial because you're either large or not, and it's discrete, right? You've got 36 of them, you want 3 or more. 3 or more means you want to go from 3 to 36. So that. Yeah, using your p-value for the binomial p, because that's the probability of a quote success being large. Nice, well done. Probability of n or more butterflies being very large is less than 1%. So it's kind of similar to here, where they said where we just figured out 3 or more was 0.29. We want to figure out what value of n would cause that to be 1%, or less than 1% specifically. There's three main ways you can go about solving this. One of them I don't really recommend, but maybe that's just because I don't understand the CAS function all that well. It's a bit ambiguous, but I guess if you have full understanding of it, it stops being ambiguous if you practice using it. So you're trying to find n. You're still binomial because you still got your sample of 36. Except this time you're not told your x information, but you're told what a probability needs to be targeting. You can use algebra. Yep. Let me just make sure I actually did do an algebra version. I did not. I did a guess and check. So as far as the algebra that you could be doing here... Oh, wait, maybe not, actually. Because n or more... Oh, I feel like you could... Oh! No. So... n or more... You can only do the algebra when you... when you have the x equals 1 or x equals 0, because you use the flip. Let me pull up an example of what I mean there. So yeah, actually you're right, algebra doesn't actually quite work for this. I'll show you why specifically. This is binomial. The algebra version of solving this is when you have these things. So, like probability of winning at least twice, an x value of 2, or at least once, right? And then you create your binomial equation because you know a lower bound or upper bound, and then you flip it to do 1 minus, because when you do a greater than, you obviously got to go up to n, but you don't actually know what n is. We don't actually even have a starting point for x either, so we can't do that. Yeah. So the only other approach there is just guess and check, really. N or more butterflies. N is our... That's a bit of an interesting choice of letter there, because we actually know n, it's 36. We don't know x, but they've labelled x as n. Bit weird. So guess and check would be the main approach there. How do we do that? As follows. So if we have a look at the camera for handwritten and the CAS, you would pull up a binomial CDF. Number of trials is guaranteed as 36. Probability of success is given to us still, because we're looking for very large, and the probability of being very large is still 0.0527. The lower bound is n, it's the thing we don't know. So this is the thing we're going to guess and check our way through. And the upper bound, because we're doing n or more, we would pick upper bound as 36, since we're going up to peak. Now, I mean, obviously if I do nothing to change the lower bound, we're going to get a probability of 1. We're going to keep choosing different values of this lower bound until we get just on the border of 1%. So, I'd pick a fairly drastic thing, walk it back a little bit, walk it back a lot maybe, walk it back a lot more. And so you kind of just get a feel for, okay, I'm getting numbers at a 0, e negative 10. I should probably be a bit more drastic with my guess and checks. We got to 3%, so you want to move it over a little bit more. 1%, a little bit over. And so, I mean, I already know at this point it's going to be 7 now, because you want to be less than 1%. But just to sort of show you, you want to be just below 1%, or at least as far as you can, close to it. And so, yeah, that's going to get you your n, or I guess in the binomial term it's your x, is going to be 7, the lower bound of it. So guess and check is the way to go there. I'm going to spend a little bit of time playing with another CAS function. If I don't get it immediately, I'll move on, because I'm not really an expert on this one in particular. Inverse binomial is nominally supposed to do this stuff. Might be this one. Cumulative probability, I'm assuming it's 0.01. Base probability of success was the 0.0527. Number of successes, no. This is the total number of trials. Must be the other one then, which would be inverse binomial for... Alright, let's just try it, see if it works. I feel like this is like an inverse PDF type thing, where we want a CDF. I don't know, let's see what happens. 36 is the n, probability of success is 0.01. Give the matrix form so I can see everything. I don't know what that's done. Alright, forget it. I feel like there is a way. I've seen inverse binomial stuff used to solve these. If you know it, then great. If you don't, then you've got a better way of doing it, because you can just guess and check pretty fast. Alright, let's leave that there. That's that. Triple I now. For random samples of 36, you now got p hat. And p hat is tracking very large butterflies. Find the expected value and standard deviation of p hat. So, expected value of butterflies that are large, standard deviation of butterflies very large. But you're doing it in the p hat way. Which, yeah, on your formula sheet if you need a refresh. These are kind of freebies, although sampling and estimation does tend to confuse people. But fundamentally these are just plug things into the formula sheet that you've got. There's no real thinking beyond it. Expected value 0.0527 is correct, yep. It's always going to be a p-value. P is always expected value for, I guess you should call it expected proportion, would be slightly more accurate. I know the exam says value, but yeah. Standard deviation 0.0372, yes, that's it. Plug and play. So once you get over the weirdness of expected proportion being the same as p, there's actually no calculation there. The rest becomes super easy, because you then shove that p back into the standard deviation formula, the sampling and estimation standard deviation formula, and that gets you what you wanted. Nice. IV. Probability of sample proportion. Okay, so probability of being between plus minus 1 standard deviation. Hang on. Oh. Probability of proportion lying in 1 standard deviation of this. So, what is that asking? What is the probability that a sample proportion of butterflies that are very large lies within 1 standard deviation of... Oh, okay, so it's just, instead of saying plus minus 1 standard deviation, it's saying, well, it is saying plus minus 1 standard deviation, but it's labelling p hat, because we know this is our p hat. So, 1 to the right of p hat, 1 to the left of p hat. What's the probability of that occurring? Don't approximate it. I know there's a 68% rule. Your number's going to come out pretty close to 68%, but rounding is going to cause a few issues, which will change that. So if you can't calculate it with normal, the next thing you've got to do is figure out, okay, how else can I calculate probabilities in a range of values? Because it's still plus minus a certain thing, it's still a domain that you're trying to find probability across. So it's going to be some sort of CDF. That's what CDFs are used for. Decimals can be a bit of a throw. Just got to remember what type of probability are we still dealing with, and then that'll hone in on, oh, it's discrete, I should do this. It's continuous, I should do this. Those are your big buckets. Then obviously within discrete you've got binomial, regular discrete, and sampling and estimation. and continuous is the what do they call it? The piecewise and the normal. Alright. Waiting time. Anyone close to an answer, or shall I jump in? You're stuck? Okay. Cool. Let's sort it out. So, between plus or minus 1 standard deviation, we figured out what the standard deviations were. So, basically I want to figure out that between E of p hat, it's got to be between plus minus 1 of the middle. So you take your value of E of p hat, and then the standard deviation, that gives you your upper and lower bound that you're trying to find the probabilities between. This is a discrete thing, and so calculating probabilities you have to use discrete methods. None of the discrete methods use decimals. So what we do in sampling and estimation pretty much always is we rely on binomial. So whenever we're trying to calculate p hat probabilities, we always say, no, I'm not going to. I'm going to convert it to x instead, and then go from there. P hat is always x on n, so to flip these, you now just got to multiply by n to get the equivalent number of things. Like for instance, if I had 1 out of 10 as my probability of a pen being red in a box, and the box had 10 pens, if I multiply that by 10, well, one of the pens in the box should be red. 1 out of 10 for red, 1 red pen. We're just flipping it from a proportion to a discrete number. This obviously needs rounding because it's decimals, and so what you would do is round inwards. You always round inwards. So in this case, I didn't really like throw anything that would cause you to do otherwise, but if this was, for instance, 3.6, you would actually have to round this inwards, because then you'd be going outside of plus minus 1 standard deviation. So this always rounds down, this one always rounds up, no matter what they say. So up to 1 and 3, and then it's just a CDF from there. So that's the only tricky thing, remembering that every time we do p hat stuff, and you're trying to calculate probabilities, shove it back into binomial, and then you can work with it a lot easier. I'm here for any questions if you have them, otherwise I'll leave you to enjoy the rest of your day. No worries. Thanks guys.